We've discussed a lot of bin sorting problems. Between combinations of balls and bins being labeled and unlabeled, we also had three possible restrictions. Maybe no bin was allowed to be left empty, maybe every bin could have at most one ball put into it, or maybe there were no restrictions. So we have two choices for whether balls and bins are labeled and unlabeled each. That's four total choices there, with three different restrictions. So between combining all of these possible choices, we have 12 different bin sorting problems, most of which we've considered explicitly. Here's a chart summing up all of the results, including a couple we didn't explicitly do. So if the bins and balls are both labeled with no restrictions, remember there's going to be K bins and N balls, there was this exponential counting. If I'm not allowed to place more than one ball into a bin, we have this ratio of factorials, but only if the number of balls does not exceed the number of bins. Otherwise, by the pigeonhole counting principle, there would be no possible way to do it. If every bin has to receive at least one ball, here's the result. If the bins are labeled, but the balls are unlabeled, we had these three results. These were all presented as one result earlier, several videos back, two of which were then proved and one of which was sort of left as an exercise, and so forth and so forth. Okay, so we've actually addressed many of these things quite explicitly, but here they are summarized. Many counting problems that you might find out in the real world can be attacked through some combination of the above as a nice starting point. And this 12-fold collection of counting problems is sometimes referred to as the 12-fold path. So let's take a look at a sample problem. You have 10 red candies and 20 blue ones. What we want to do is make a line of 12 candies. But note that different red candies cannot be distinguished and different blue candies cannot be distinguished, but red and blue are certainly distinguishable. So I have 10 red and 20 blue. Since I'm making 12 candies in a line, I can't, for example, make them all red because there's only 10 red candies to choose from. So how many possible ways can I put 12 candies in a row where they have to be drawn from this collection down here? What we're going to do is we're going to count how many red candies we grab. Well, since I'm making 12 candies in a row, if I grab I red candies, then 12 minus I is how many blue ones I have to use. Now the reason we're picking red candies rather than blue ones, if I let I be the number of blue candies, I could say I count 12 minus I red ones, but then we'd have to be a little careful because if 12 minus I is the number of red candies, that can't be larger than 10, and we'd have to put restrictions on how many blue candies we grab. By counting I as the red candies, it's going to be a little more straightforward. We simply say 12 minus I blue ones, and since there's 20 blue ones to pick from, I don't have to be too careful about this. So now I have 12 candies. I have I red ones and 12 minus I blue ones. The number of ways to put them in a line is 12 choose I. I choose out of the 12 spots I of them for the red candies. The rest are then automatically blue. How many choices of I are actually legitimate? Well, the number of red candies I can pick is anything from 0 to 10. So overall, the ways to put 12 candies in a line, if they have to be drawn from the collection below, is to sum from I going from 0 to 10, 12 choose I. As I goes from 0 to 10, pick I red candies and 12 minus I blue ones, and then from the 12 positions, choose I spots for your red candies. Sum up over all legitimate choices of how many red candies you use. If you then compute out the sum of all these numbers, 12 choose 0 plus 12 choose 1, and so forth, all the way up to 12 choose 10, the result is 4,083. There are 4,083 ways to make a line of 12 candies that are drawn from this collection. Another example. I have a class and it has 13 tall students and 11 short ones. All students, however, can be distinguished, usually. So how many ways can we make two teams of 10 students each? So there are 24 total students, but I'm only making two teams of 10. However, I do require that each team has an equal number of tall and short students. So if the first team of 10 students is made with 5 tall and 5 short, then the second team must also be made from 5 tall and 5 short. Let's let I be the number of tall students on each team. Well, it has to be the same between both. So if I is the number of tall students on each team, then 10 minus I is the number of short students on each team. So first, of the 13 tall students, choose I of them to go into one team. That's 13 choose I. Then let's choose 10 minus I short students to go into the same team. Of the 11 short students, I choose 10 minus I of them. So there were 13 choose I ways to make tall students, and 11 choose 10 minus I ways to pick short students. Next, I need to choose I tall students to go into the second team. But I've already picked I tall students for the first team. I did that back here. So there's only 13 minus I tall students remaining. So from the 13 minus I tall students, I choose I of them and I put them into the second team. Similarly, because I've already chosen 10 minus I short students to go into the first team, there's only 11 minus 10 minus I short students remaining, from which I can choose 10 minus I to go into the second team. And this top argument here, 11 minus 10 minus I simply distribute the minus sign and simplify. That's going to be an I plus 1. So overall, first choose I tall students out of 13 for the first team, then choose 10 minus I short students out of the 11 short students for the first team. And then, from the remaining 13 minus I tall students, choose I of them to go into the second team. And from the remaining I plus 1 short students, choose 10 minus I of them to go into the second team. Since these 4 tasks were all completed in sequence independently of one another, we just take their product. So continuing, we've discovered there are this many ways to make a pair of teams with I tall students on each team. But we actually overcounted. Okay, we aren't really distinguishing first team and second team. The teams themselves cannot be distinguished. In other words, if exactly the same students are in team 1 versus team 2, and then I just switch them to be team 2 and team 1, I've fundamentally made the same teams. I've simply changed which one I made first versus which one I made second. So any possible way of making the 2 teams could have been first team and then second, or second and then first. They've all been counted twice. So I need to divide this result by 2 to account for that. Also, we had I being the number of tall students. Since I tall students go into each team, there are 2 I tall students altogether. There were only 13 tall students in the class. So if I need to use 2 I tall students, I can't have I be larger than 6. If I tried to put 7 tall students into each team, I would need 14 of them total, and I don't have 14 tall students. So I can only go between 0 and 6. But in fact, once I used I tall students, I needed 10 minus I short students per team. So that's 20 minus 2I short students altogether. But since there were only 11 short students in the class, 20 minus 2I cannot be larger than 11. So I can't be smaller than 5. If I was 4, I would get 20 minus 8, and that would be 12. I would need 12 short students if I only put 4 tall students into each team. I don't have 12 short students, so I have to put at least 5 tall students on each team. So I can't put more than 6 tall students on each team, and I have to put at least 5 tall students on each team. Well, that really narrows it down. So the only number that I can possibly pick as the number of tall students is 5 or 6. So now we can simply sum up the number of possibilities. If I is 5, we get this right here. And don't forget, we needed to multiply by a half to account for that overcounting. But if I is 6, we get this right here. And this also needs to be divided or multiplied by 1/2. If I compute all of this out, it turns out to be this number right here. So even though I didn't have that large of a class, 13 tall students and 11 short ones, and I wanted to make 2 teams of 10 with a restriction that the number of tall and short students had to be the same between the 2 teams, I still see there's about 169 million different ways I can do that. That's a lot. Let's take a look at another example. I've got eggs. There are 12 white eggs and 4 blue ones, but nothing is labeled. What I need to do is I need to put them into 4 unlabeled bins. Now the restriction is that no bin is allowed to have more blue eggs than white ones. How many ways are there to distribute the eggs according to these restrictions? So equivalently, what we're saying is that we have to distribute the white eggs, making sure that every bin gets at least 2 of them, because if a bin only had 1 white egg, it would have to get 3 blue ones, and then I'd have more blue than white. There are no labels on any objects though, so restricted partition numbers are the closest tool we have. That was unlabeled objects, unlabeled bins, but since I have to use exactly 4 bins, a restricted partition number makes more sense. So since each bin has to get at least 2 white eggs, each bin will definitely not be empty after distributing the white eggs. So once I distribute the white eggs, and all the bins have at least 2, what we need to do are count all the ways to split 12 unlabeled objects into 4 non-empty sets. What we're going to do is we're going to proceed by listing the number of white eggs in a bin from largest to smallest. So continuing with our egg counting problem, here I am accounting for largest to smallest, distributing the white eggs. 9, 1, 1, 1, 8, 2, 1, 1, 7, 3, 1, 1, 7, 2, 2, 1, and so forth. This is going to be all the ways to make a total of 12 objects where I make sure I'm going from largest to smallest. And there they are, okay? But now we've already remarked that we can't have any bins that only have 1 white egg. So if there are any 1s in an arrangement, that's not going to work out. So get rid of all of those. Okay, we can also get rid of any arrangement in which a bin gets more than 4 white eggs because we were specifically required to make 4 different bins of 4 eggs each. So I'm not going to put 9 white eggs into a bin. So many of these are eliminated. As far as counting the distribution of white eggs into bins, what we did is we said partition the number 12, the number of white eggs, into 4 non-empty sets, the number of bins, and then eliminate any in which a bin has more than 4, but also eliminate any in which a bin has 1. And we're only left with these 3. Now all we have to do is fill in the remaining spots with blue eggs. There are only 3 possible arrangements. So this was actually much smaller than the previous problem. It was much more restricted, requiring ourselves to use 4 bins and requiring the number of blue eggs to not outnumber the number of white eggs really cut down on the number of possibilities. We could have also done this problem in a sort of mirror universe version where we count the blue egg distributions. What we need to do is distribute 4 eggs into bins, but we're not required to put blue eggs into any bins. But we do need to make sure that no bin has more than 2. So we can do the following. Okay, we're allowed to use zeros now because there was no requirement to put blue eggs into a bin. But I could do 0, 0, 2, 2, 0, 1, 1, 2, and 1, 1, 1, 2. I'm not allowed to put more than 2 blue eggs into a bin because then they would outnumber the white eggs, and that was our real only restriction. And this is just an exact mirror of the ones we found on the other side. 0, 0, 2, 2 for the blue eggs versus 4, 4, 2, 2 for the white ones. 0, 1, 1, 2 for blue versus 4, 3, 3, 2 for white. And 1 blue in each versus 3 white in each.